Chapter 19 deals with magnetism. So magnetism is a special property. It's a special type of force. Now, everyone's familiar with magnets. You've seen magnets. So a substance that attracts or pulls on other substances. So you see that some things are naturally magnetic and some things are not. So examples are iron, cobalt, nickel. These are magnetic. Now, you can demagnetize them by doing certain things, heating, hitting them. We actually have a magnetizer, so the magnets we're going to use today in the lab, somebody magnetized them the other day. So things that are non-magnetic, tin, copper. So you see that just because something is metal, that doesn't mean it's necessarily magnetic. Now, what makes something, well, we'll talk in a second about what makes something magnetic. So magnetic force can also repel, push away. So every magnet has a pole. So the ends of the magnet, there's a north and a south pole. And this is extremely important to understand the characteristics and properties of magnets. So we all learned this in elementary school, that like poles repel one another and unlike poles attract, just like charges. Okay? So things are magnetic. It's not just the way the atoms line up. If we talk about other things, we know that things are magnetic because of one thing. It has to do with the electrons in the individual atoms. So we know that materials are made up of atoms. Within atoms, we have protons, neutrons, and electrons. Well, the electrons are in the outermost energy level. We know the electrons are moving around the nucleus. Well, electrons do two things. They revolve and they rotate. Now, in normal materials, the electrons, as they're revolving around the nucleus, they're all rotating in different directions. So rotate means to spin on its axis. Well, in things that are magnetic, all the electrons rotate in the same direction. So because the electrons in the atoms are all rotating in the same direction, that causes it to have this physical property, which is to be magnetic. So again, so magnetic domain is a region composed of a group of atoms whose magnetic fields are aligned. So that's what I mean by aligned. So what happens is when all the electrons are all rotating in the same direction, it causes the atoms to line up and go in the same direction, which then causes it to have magnetic properties. So remember, magnetism goes all the way down to the rotation of the electrons within the atom. And then your book kind of skips over that part, so your book goes right to, it just causes, magnetic domain. Things are magnetic when it looks like this, when all the atoms are lining up in the same direction, but it's causing by the rotation of the electrons. Okay? So materials can be classified as a temporary or permanent magnet, and whether it's hard or soft, depending on how long it retains its magnetism. So permanent magnets, these are made from a material that's magnetized and creates its own magnetic field. And a magnetic piece of material is classified as either hard or soft, depending on to the extent. So soft ones, they're easily magnetized, but they can lose their magnetism easily. And then hard is one that it's like a permanent magnet where it keeps its magnetism a lot longer. Now, when we look at a magnet, and you probably did this in middle school, where you cannot see the magnetic field that exists around a magnet, but it exists. Just like, can we see the gravitational field that exists around something? So magnetic fields exist. We can't see them. Now, to help us see them, what a lot of times someone does is you can take a magnet and you can put a pair of clear acetate over it and sprinkle iron filings, and the way the filings line up gives you an idea to picture the magnetic field. So the magnetic field exists, but it's not something that's visible with the human eye. So the space around the magnet where a force is noticeable. Now, again, this has to do with distance. So the further away you get, the weaker the magnetic field. Now, there's a lot of symbols and there's a lot of notations that we need to know in order to understand magnetic fields. So to represent the direction of a magnetic field in two dimensions, we use dots to indicate that it's out of something and X's. So let's say I had a magnetic field that was pointing down into this piece of paper. If it was going into the piece of paper, I would have an X. If it was coming out of the piece of paper, I would have a dot. Okay? So this is the convention that we use. So this is into the page and out of the page. And if it was going up or down, you would see we would just use an arrow. Now, if we want to look at the magnetic fields, these are the pictures that we would see. So first of all, we need to know that magnetic fields, remember when we learned about electrons and protons? Well, now we're looking, instead of looking at an electric force, we're looking at the magnetic fields. So we can see the magnetic fields that exist around magnets. They always come out of north and into south. So if I had two magnets that were side by side, what's going to happen is it's going to come out of the north and go towards the south. Now, what if I had two magnets and I put the poles the same, north and north? Well, we know that like poles repel one another, so there's going to be a force of repulsion, but because it's north, you see how the lines are coming out and going out like this? But if I had two south, do you see with south, even though they're repelling one another, see how they're both going in? What if I had a horseshoe magnet? So for a horseshoe magnet, again, it's going to go out of north and into south, so it would look like this. Now, what if I just had a plain bar magnet, which we're going to use today in our lab? Well, the bar magnet shows it's still going to go out of north and into south, but then there's parts of the bar magnet that we would see like this. So you would see the lines of force going from one end of the magnet to the other. Now, what if I have a magnetic piece of wire, a long, skinny wire, or something like that? So magnetic induction in the vicinity of a straight wire is directly proportional to the current in the wire. And it's inversely proportional to the distance from the wire. It almost sounds like other things that we've learned. A uniform magnetic field into or out of the plane of the paper. So let's say, remember, a dot means what? Out, and this means into. So if I had a magnetic field to represent a magnetic field going in a certain direction, if it was going out of the page coming up like this, it would be a bunch of dots. And if it was going into the page going down like this, it would look like that. But if it was going up or down, I would show it with arrows. So magnetic flux, this is equal to AB cosine theta. When you get to college, there's no problems in your book like this. We don't need to know this for the homework. They introduce in the book. I'm just putting it out there for some of our homework. We do not have calculations like this because we end up, everyone in this class has not learned in their math class dot and cross product. So there's not calculations. All right, so Earth acts like a magnet. So today we're actually going to use magnet, and we're also going to use a compass having geographical directions, north, south, east, west. And it's going to point to magnetic north. Is magnetic north the same as geographic north? Where's geographic north? The North Pole, right? But magnetic north actually points towards Hudson Bay, Canada. So that's where the compass is actually, that's where the magnetic part of the Earth is. And we're going to talk more about that in detail next week. So in 1820, there was a physicist, and he discovered that a wire carrying a current actually produces a magnetic field around the wire. Now, when we're understanding magnetic fields, we start to get confused because we have a force going one way, we can have a speed of something going another way, so we have to establish certain rules, which is a sign convention for understanding the direction. Because whenever we talk about force, we know that any force is first of all measured in what unit? Newtons. We also know that forces have both magnitude and direction. So this is the part that gets to be a little tricky. So this is something called the right-hand rule. So it says the thumb of the right hand is pointing in the direction of the current. So see in this picture the current's going up, you would take your right hand and you would put your thumb up in the direction of the current. The fingers of the right hand, from the wrist to the fingertips, will curl in the direction of the magnetic field. So what that means is if the current is going up, the magnetic field is going this way around the wire. If the current was going the other way, the magnetic field is going the other way. So there's 3 right-hand rules that we're going to learn. And I'm going to show you what happens is on your homework that, and I wrote note, if you use electron flow instead of conventional current. So electrons, if we're talking about electrons, what's the charge on an electron? What's the charge of an electron? Negative, that's right. So if you're using an electron, you're not going to use your right hand, you have to use your left hand. So if the charge is negative, you use your left hand. And we're going to see that in 2 of our homework problems today. And if you don't use your left hand instead of your right hand, your sign convention ends up being wrong. So just remember, for negative charges, you use the left hand. So we can find magnetic fields, again, around the wires. So this represents the current. So this shows you the magnetic field around the wire, which direction it's going. And this is showing it like on a piece of paper to help you conceptualize. So remember, this is going in, this is coming out. So if we were looking at a coil, this is the current going through the coil, and this would be the direction of the magnetic field. If you have a number of loops together, and you have something called the solenoid, and we'll talk more about that, and this is the way the magnetic field would look like this. So the magnetic field around a solenoid, see how it's lots of loops? You've probably noticed I have a giant, well that's something else, but it's very similar in the back to demonstrate. It looks like a magnet, but then we have the fields around the individual small loops, like this. So if we were looking at that again, for the right hand rule number 2, the fingers of the right hand are wrapped around the direction of the current, and the thumb will point in the direction in which it's moving, so we know which way the field is acting. Okay, for our homework tonight, the first equation we need to know is this one. So this has to do with the magnitude of a magnetic field. So the unit for magnetic field is B. It's capital B. It's measured in a unit called a Tesla. Ooh, that sounds familiar. Tesla is named after Nikola Tesla. Now you all know who he is. And the unit for a Tesla is a capital T. So magnetic field is equal to this is the magnetic force. Now, since we're just doing it in the beginning, you can just, in the beginning called it F magnetic. So if you want to abbreviate it, F subscript M, F subscript MAG. And this is equal to Q divided by V. So Q is the charge in coulombs, and V is the speed of the charge. Now, a lot of times you want to say, how do the units end up canceling? Well, a Tesla is actually a Newton divided by a Coulomb times a meter per second. So if we're going to carry our units through and cancel them, you know how the units always end up. Now again, when you're using this equation, you have to be very careful. When you're reading a problem, if it says a proton is what charge? Positive, so you're going to use your right hand. If you're using this equation and it says an electron is a negative charge, and you're going to use your left hand. And remember, that's one of the things that you remember, that the charge on a proton and electron is 1.6 times 10 to the negative 19 coulombs. It's positive if it's a proton, it's negative if it's an electron. So if it's a proton, use your right hand. If it's an electron, use your left hand. This is a really long example for just a really simple calculation. But the reason is that I put a lot of explanation in. So it says a proton, so that means it's positive. That means I'm going to use my right hand. Having a speed of 5 times 10 to the 6 meters per second in magnetic field feels a force. So again, I didn't do it here. I just noticed I need to write my given. I'm given V. I'm given F. And it says, when moving horizontally, determine the magnitude and direction of the magnetic field. So the charge on a proton, 1.6 times 10 to the negative 19. Since the proton feels no force when moving north, the field must be in a north-south direction. So again, we're going to use the right-hand rule. We put our fingers in the direction. Your thumb points west, and the fingers is found, and the magnitude of the magnetic field, again, B is equal to F over Q. If you want to find F and they give you this, you rearrange the equation to solve for the unknown in terms of the known. Now we have one more equation, the magnetic force on a current carrying wire. So this equation is F is equal to, I say BIL. This L is a different L because this has to do with magnetism, so this is actually a script L. So it looks more like this, not like that. When I was typing the notes, I should have changed the font there to whatever I did the font here. So, and here's a diagram here. So if the magnetic field is going this way, the current is going up, the force is going to come out of the page. So sometimes it's difficult when you're dealing with more than one dimension to show that on a flat piece of paper. So here's an example here. How much current is flowing in a wire 4.80 meters long if the maximum force on it is 0.75 newtons when it's placed in a uniform 0.08 Tesla field? So we write our given, we write what we want to find, we rearrange the equation to solve for the unknown in terms of the known. So S is equal to ILB, but I want to solve for I, the current, so I rearrange the equation, so I'm giving everything. So that just gives me the magnitude of the current. So if I want to find the direction of the force on the wire, again, you use this as right-hand rule number 3. So here's a picture of your hand. The current is the thumb. B is going to be the fingers, and then F is going to be the palm. So whenever you're using the right-hand rules, whatever one it is, the fingers is always going to be B. The way your palm is always going to be F. The difference is this way it's current, and the first one is going to be the velocity. Okay? So you have to practice. What if we had forces between parallel wires? So what if instead of we had one wire, we had 2 wires next to each other? So when we have wires next to each other, so you see up here I have 2 wires, the arrows represent the current. So the current's going this way, and then that shows the field. So this is what it would look like here, and then also what would happen if we were looking at it in terms of magnets. So what if we had 2 magnets side by side, and then here they're going in opposite directions?